Astronauts aboard NASA's Apollo 8 mission in 1968 witnessed something that was supposed to be unimaginable. Hey everyone, welcome to Fly Me to the Moon. We are back with another video entitled, Why the Next Moon Mission Could Fail. How we're screwing up space travel. Let's begin. Every day, just before the lunar dawn and sunset, they observed a haze forming on the horizon. Then, just before the sun rose or set, they observed dazzling bands of light shooting out from the surface and rapidly growing into the night. Due to our atmosphere's ability to refract sunlight, we experience these brilliant rays twice daily on Earth. The moon, however, lacks an atmosphere. The region just above the moon's surface is essentially a vacuum. While there are trace concentrations of some noble gases like helium and argon in the outer lunar atmosphere. So, from where did these light bands originate? Dust, not air gases, hold the key to the problem. The Apollo astronauts noticed a phenomenon created by layers of microscopic moon dust that had been thrown off the moon's surface, scattering light. This might have been a stunning sight for the astronauts of the Apollo missions, but lunar dust also has a negative side. Gene Cernan, the last person to walk on the moon and the end of the final Apollo mission, said after it concluded, quote, "I think dust is certainly one of our largest barriers to a regular performance on the moon." But before we move ahead, why don't you follow Fly Me to the Moon and land your lunar module on that bell icon for more updates. Now back to the good stuff. We now have an extremely good understanding of just how harmful lunar dust can be, thanks to the reports from the Apollo program, as well as an examination of spacesuits, gear, and other items after they'd come back to Earth from the moon. The dust dramatically reduced the visibility of astronauts during moon missions and damaged pre-existing industrial equipment and artifacts on the surface of the moon because, once blasted by the massive explosion from trying to land the spacecraft, it discovered its way into NASA components, irritating the astronauts' eyes, noses, and lungs, as well as covering screens, breaking watches and camera systems, and corroding equipment as well. Do you know why Mr. Moon split up with Miss Sun? Well, because Moon never wanted to go out with her at night. But Hey, I'm sorry I put you through that. So in spite of my awful joke, I'm asking you to like, share, and comment on the video. And subscribe to Fly Me to the Moon. You can also comment on my karaoke or my awful jokes if you want to. Hose locks and zippers got much harder to operate. The suit's mobility decreased. It was harder to read the life support system displays. The visors got scratched, the electronics got hot. There were more leaks in the suits, which resulted in pressure losses. Additionally, despite their best efforts to eliminate the dust in the lunar module utilizing vacuums and brushes, astronauts continued to deteriorate with time. The Apollo 17 crew spent the greatest time outside of the lunar lander, but they only completed 22 hours of surface EVAs, causing the spacesuits almost irreversible damage. Had they spent longer working on the surface of the moon, the suits would have just finally been worthless. However, 22 hours is a mere fraction of the time needed for any upcoming expedition to the moon. One major and extremely ambitious aim was identified by NASA in 2015, when it unveiled its space technology roadmaps. For a total of spending 800 hours on the moon's surface, or about 37 times as long as the Apollo 17 astronauts spent outside, they needed their spacesuits to withstand 100 extravehicular activities. This issue could make or break a long-term presence on the surface of our moon greater than any other issue facing NASA or any other space organization. But how could you even start to make a spacesuit last that much longer? As a result of this debris shower, pieces of lunar rocks break off, covering the lunar surface in a fine coating of dust. This presence of specific hits can sometimes be so powerful that they melt the soil's mineral content and turn it into glass. There's no water in the soil or air to bind the nanoparticles collectively, and there's no biological degradation via wind to dull the jagged corners, making lunar dust a mixture of very small particles and razor-sharp glassware. Ooh. Therefore, it's clear that this will not work well with the complex mechanics of the lunar spacesuits. Due to the shattered glass inside the dust, it can readily scratch glass or conductive materials. The dust is sufficiently small enough to pass through practically any space. On the side of the moon that faces the sun, dust motes are struck by X-ray and ultraviolet light, which knocks electrons off and causes positive charges to form on their surfaces. Then the opposite occurs on the side that is protected from the light. The atoms become attracted to the negative by absorbing electrons from solar winds. Electrostatic possibilities on the lunar surface can reach up to 20 volts during the day and an astounding negative 3,800 volts during the night due to both the positive and negative ions on the atoms. So when Apollo 8 astronauts observed the stunning bands of light at dawn and dusk, they were viewing the passage of light through a section of fine dust that had been electrostatically levitated from the moon's surface. Dust particles with like charges repel one another and are attracted to the lunar surface, producing a fountain of pointed microdust that goes up above the horizon. The same dirt that the Apollo astronauts stepped in and churned up while they worked just outside the lunar module adheres to their suits in a similar way that a statically charged balloon sticks to your clothing. One of the key factors contributing to the dust's annoyance is a charge, but another factor could be how to get rid of it. As part of the revolutionary, innovative, and game-changing idea competition in 2021, NASA challenged university students worldwide to provide original solutions to the lunar dust issue. Conduit fibers modeled after chinchilla hair, an electrical charge brush UV rays might operate, and fabric for spacesuits that resembled how some insects employ hair-like elements to gather and release pollen were a few of the successful proposals. These concepts handle the same issue in various ways, but they all take the same general strategy of employing charge to either quietly or aggressively remove dust from spacesuits. How can the charged particles be made to resist rather than attract the outermost part of the spacesuit? NASA developed a sophisticated solution. They chose to develop a technology that could be successfully incorporated into the existing layers of fabric and materials present in the current generation of spacesuits rather than fully rework the suit's outer layer. The team planned to develop a suit that could generate its electrical charge and actively evacuate dust, serving as an energy barrier. The first difficulty was deciding on the electrical conductor that would be used to make the electrodes. This technique for ejecting dust was not novel. It was modeled after the electrodynamic dust shield technologies that NASA had employed on solar panels, sensors, and heaters since the late 1960s. The electrodes, constructed of silver, copper, or an indium tin alloy, were mounted on fixed, solid bodies in most of these instances. As the astronaut flexes their torso or legs, the interlocking fabric pieces in the outermost surface of the spacesuit roll over one another at the joints. Therefore, even if the silver and copper electrodes utilized in the earlier EDS systems may have been good electrical conductors, because, to their poor flexibility, they wouldn't even be able to withstand the wear and tear brought on by the joint's frequent flexing. These scientists are now centering on three key health risks: the long-term impacts of space radiation, vision depreciation disorder caused by the increased stress on the mind, and optic nerve swelling and retinal changes, changes in the shape of the eye with an increase in intracranial pressure. And another issue is the effects of isolation on psychological health, which may make full recovery all but impossible. But humans have a way of overcoming great challenges like this. So let's not end on a down note. Thank you for watching this video. I hope you learned something. Please comment if you want to add any other points. Also remember to like and share the video and subscribe to our channel. Fly me to the moon. We'll see you in the next video. By the way, check out the other exciting videos on our channel.